In this video, we are starting our section on Taylor and Maclaurin series. So our goals are to approximate functions using what are called Taylor polynomials, determine the Taylor and Maclaurin series of a given function, and once we already have some series, we can derive new ones, either by substitution or by doing algebraic manipulations. Later, we'll get new ones by differentiating and integrating known series. So let's start by talking about Taylor polynomials in series. So the question I want to begin with is, how can we calculate something like e to the 0.2? And my first idea is, if I look at my graph of y equals e to the x, this exponential graph here, I can use a tangent line to approximate it at some nearby point. So I know that if I plug in 0 into e to the x, the y value is 1. So what I'm interested in getting is, if I were to plug 0.2 in, I want to know, well, where is that output on the e to the x graph? And I don't know, but I can approximate it by looking at this tangent line, which I can figure out its equation, and plug 0.2 into that tangent line to get this approximation, which isn't equal to the exact value, but it's pretty close. So when I get this tangent line, it's a degree 1 polynomial. And let's remember, to get the equation of a tangent line, I need to first find the slope. So if I do y prime, my derivative, that's just e to the x. And now if I plug 0 into this, y prime of 0 is e to the 0, and that's 1. So then the equation of my tangent line, I'm going to get y equals, the slope is 1, so I get y equals x, and then plus the y-intercept is also 1. So that's the equation of my tangent line. And if I want to know what happens when I plug in 0.2, if I plug that into this, I would get 1.2. And that's my approximate y value. It's not equal to the exact value, but it's an approximation. So now I'm going to try to get a better approximation using a higher degree polynomial. So a tangent line is a degree 1 polynomial. I'm going to pick something higher. In my example, I'm going to work it out with degree 5, but I could pick whatever degree that I want. So here's a formula for a degree 5 polynomial, where I don't know what these coefficients are. I really want this polynomial, which can now curve. It doesn't just have to be a straight line. I want it to match e to the x as much as possible. And I'm going to use the idea of the tangent line to help guide me. So I notice that both of them go through this same point. So I want that to happen with this polynomial in e to the x. So when I plug in x equals 0, I need the output to be the same. So if I plug 0 into my polynomial, most of these terms just become 0, and I'm just left with a naught, this first coefficient. When I plug 0 into e to the x, I'm just left with 1. So those have to be equal. A naught's got to be 1. That's guaranteeing that, hey, they go through this same initial point. Now I'm going to make their slopes match, just like what happened with the tangent line. And to do that, I have to do the derivative of both. So my polynomial derivative is here. Derivative of e to the x is just e to the x. And to get the slope when I plug in 0, well, if I plug 0 into this, all these terms at the end just become 0. And I am left with just a1. If I plug 0 into e to the x, I'll get 1. So those got to match. That means a1 is 1. So at this point, I know my first two coefficients. So what having a higher degree polynomial lets me do is, now I don't just want to match this point and the slopes. I also want to match how they're curving in more detail. And I can get that by doing more derivatives and setting them equal. So if I do the second derivative and I plug x equals 0 into this, in my polynomial, I'll just be left with 2a2, because everything after that just becomes 0. If I plug 0 into e to the x, because that's the second derivative, I get 1. So matching those, 2a2 equals 1, and then dividing 2a2 is 1/2. Okay. And if I do the next three derivatives, which I have here, and now I plug 0 into those, and also into these subsequent derivatives of e to the x, I'll get these equations after I plug 0 into both of them. And then isolating a3, I get it's 1/6. Isolating a4, it's 1/24. And then a5 is 1/120. So at this point, I have all of these coefficients of this polynomial. And there's something I want to notice about all these denominators. They have this nice pattern. I want to have you give the video a quick pause for 1 minute. See if you can figure out what the pattern is with those denominators. In 3, 2, 1, pause it and think about that. All right, so let's talk about it. Well, I noticed that 2 is 2 factorial, and 6 is 3 times 2 times 1. That's 3 factorial. 24 is 4 factorial. And 120, that's 5 factorial. So you get all these factorials on the bottom. And that's not a coincidence. The reason why that's happening is, like for example, when I took this term, and if I did 3 derivatives, so if I did the first derivative, this 3 is going to come down. It'll multiply here, and then the new power is going to be a 2. When I do the derivative again, the 2 is going to come down, and I'll subtract 1 from that. That'll give me a 1. And then I do another derivative. The 1 is going to come down. Ooh, there's the 3 factorial. The new power is going to be a 0. So I'll get x to the 0, and that just becomes a 1. So that's why you get this 6 that I had here. And it's the same for each of these other terms once I do enough derivatives. So if I take all those coefficients and I plug them in, well, I get this e to the x is approximated by this polynomial. So if I want to plug in 0.2 into both sides, I can. And if I use a calculator to estimate this, well, this right-hand side ends up being approximately 1.22140267. I'll put a dot because it keeps going, but those are the first 8 decimal digits. And then if I do that with e to the 0.2 using a calculator, this starts off very similarly. I get 1.221402, but now it's going to be different. Then it's a 7, and then it's a 6, and then it keeps going. So they match actually really, really closely. So there's a couple reasons why I would expect something like this to be a pretty good estimate. One is I'm using a higher degree polynomial, and matching all these derivatives of my polynomial with the derivatives of the original function, it's more closely matching how this polynomial curves and sort of hugs this e to the x graph. And then the other reason why it's pretty good is that 0.2 was really close to this point I was using 0, this like reference point I was matching on. And the closer it is, generally the better the approximation. Okay. So now I want to take a look at Desmos to compare the graph of e to the x and this 5th degree polynomial. So what I have here is just a Taylor polynomial first of degree 1, which is a tangent line. And if I increase the degree by 1, if I do one extra term, I get a quadratic. And I notice that's closer to e to the x. And if I do another term, ooh, cubic is even closer. A 4th degree hugs it closer, and a 5th degree is what I had. So when I was plugging in 0.2, I noticed that they're kind of right on top of each other here. And I really, really have to zoom in pretty far before I notice that, okay, they're not exactly the same. They do actually separate out a little bit. And that's what I was noticing when I did my example. They were pretty darn close to one another. So let's zoom it back out. Let's zoom this thing back out. And I want to briefly take a look at, well, what happens if I did more terms? I'm expecting my polynomial is going to more closely match e to the x. So I'm going to just let this slider play. So if I go, now I'm at 20, now I'm at 30. Maybe I'll pause it here. 45, and now 45 degree, and that they're pretty darn close. And the more of these terms that I take, the closer my approximation gets. And in fact, if I take an infinite number of terms, an infinite polynomial, they will exactly match, which I think is pretty cool, pretty remarkable. So what we've done here, I can give this a more general definition. What I say, so the nth degree or nth order Taylor polynomial of f of x centered at x equals a, it's this polynomial that's given by this type of formula, where I have all these like x minus whatever that center point is to a power. I have terms like that. And the coefficient of this term involves doing the nth derivative of the function, plug into that center point, which is what I was doing in that last example. And you end up dividing by n factorial, which again, I was doing in all of these. So this is going to approximate my function near whatever that center point is. And in constructing it, it ensures, hey, when you plug in that center point into both, it's going to be the same. And when you do any of the derivatives up until the nth derivative, and you plug in that center point, they all need to match. If I kept going and added infinitely many terms to this polynomial, we get what's called a Taylor series for the function. So here's what that looks like for e to the x. And I can write this in sigma notation. In fact, I want to have you practice this. So give the video a pause for maybe 30 seconds and see if you can figure out what the formula is that goes here. In 3, 2, 1, pause it and try that. Okay, let's talk about it. So on the numerator, I have all these powers of x. So I will write x to the n. On the denominator, I notice I have a factorial that matches what the power is. So if my power in sigma notation is n, the denominator's got to be n factorial. Anytime I get my sigma notation formula, it's helpful to plug in the first couple of values for n to see does it match the first couple of terms. So if I plug in 0, I'll get x to the, I get x to the 0 over 0 factorial. Well, x to the 0 is 1, and then 0 factorial is 1. Oh, and that does match the first term. If I plug in 1, I get x to the 1 over 1 factorial. Oh, that does match that next term. And it'll keep going like that. So that's good. So, before I keep going, I think it's helpful to at least do a reality check about this, about like, why do I expect this weird infinite polynomial to be kind of close to e to the x? Because it actually turns out this Taylor series actually is exactly equal to e to the x, not even just an approximation. And not only that, it's exactly equal for any x value that gets plugged in. So we'll show why that is in the next section, but I can at least get an intuitive sense of why I expect that to happen here. So one of the things I know about e to the x is when I do the derivative, you just get itself. So that means with this polynomial, if you do the derivative, you should get itself. So let's test that. If I did the derivative of the polynomial, well, the derivative of 1 is just 0. And then x over 1 factorial, that's just x. So the derivative of that is just 1. With this next term, when I do the derivative, the 2 is going to come down, and I'll be left with a 1 up there. 2 factorial is 2 times 1. And then the 2's will cancel. So that leaves me with x to the 1 up top, and then just 1 factorial on the bottom. Similarly, with the next term, the 3 is going to come down. So the 3 is going to come down. It'll leave me with a 2 up there. And then 3 factorial is 3 times 2 times 1. So the 3's will cancel. And I get x squared over 2 factorial. So x squared over 2 factorial. And it'll keep going like this. But I think that's enough of these to see, hey, this is matching what I started with. And that makes sense based on the derivative of e to the x should be itself. So the general definition of a Taylor series is that it's an infinite polynomial. And if I want to center this Taylor series at x equals a, now instead of just having like x squared and x cubed, you could have like x minus whatever that center point is, squared and whatever, and you keep building up higher and higher powers. Where these coefficients, the way you get a formula for the coefficients is you take whatever the power is, you take that derivative of the function, you plug in the center point into it. In the e to the x example, that center point was 0. And then you divide it by n factorial. So here's what this looks like in sigma notation. So if I plug in 0 into this, well, this becomes the 0th derivative of f. But the 0th derivative, if I haven't done any derivatives, that just means the original function. And if I plug 0 into the denominator, I get 0 factorial. And 0 factorial is defined to just be 1. So if I did that, that does give me this first term. It just gives me f of a. Because x minus a to the 0 would just be 1. Okay, so I have my Taylor series definition, and I want to end by doing an example. Let's find a Taylor series for ln of x, but centered at x equals 1. So what this wants me to do is express ln of x and approximate it using this infinite polynomial, a0 plus a1 times x minus 1, because that's my center point 1, and then I'll get plus a2 times an x minus 1 squared plus dot dot dot. I would keep going like this. So I'm going to use this formula for the coefficients. Usually in a problem where I have to get a Taylor series, Typically the problem, if it's on a homework or on a test, will specify, well, how many coefficients to solve for? And once I've done those, then put a plus dot dot dot. And then it also will specify whether or not to do it in sigma notation. So here I'm going to get up until A4 and also write it in sigma notation. So if I use this formula for A naught first, well, actually before I write that, A naught will involve getting my original function f of x, which is ln of x. And then A naught, if I plug 0 into this, I'll get the 0th derivative of f, plug in the center point 1, over 0 factorial. Well, the 0th derivative is just the original function, so I want to plug 1 into that. Ln of 1 over 0 factorial is 1. Ln of 1 is 0, so I get 0 over 1, which is 0. That's going to be this first coefficient. So to get the next coefficient, I'll have to do the derivative of f of x. So f prime of x is 1 over x. And now, to get a1, if I plug 1 into this, I got to do the first derivative of f, which I could also just write as f prime. And I'm plugging in 1, the center point, over 1 factorial. So if I plug 1 into this, I just get 1 over 1 factorial, which is 1. And 1 over 1 is just 1. So that's going to be my next coefficient. So I want to keep going now and get up until A4. I want to have you pause the video for 3 minutes and see if you can get those next 3 coefficients. In 3, 2, 1, pause it and try it. This is actually the most important part of the video. It's a chance for you to see, how well do I understand this right now on my own? It's totally fine to get stuck with it, but if you do get stuck, refer back to this formula and see what we did to get the ones we have so far. Okay, so hopefully you did that. Hopefully you tried to get those next 3 coefficients. I'm just getting myself ready because now I need to do the second derivative, which ends up being negative 1 over x squared. The third derivative is 2 over x cubed. And the fourth derivative is negative 6 over x to the 4th. So to get a2, if I plug 2 in for n, I'll get the second derivative of f, plug in my center point, over 2 factorial, and then a3 is similar. I'd have to do the third derivative, plug in the center point, over 3 factorial. And then a4 would involve doing the fourth derivative, plug in the center point, over 4 factorial. So if I plug 1 into the second derivative here, I get negative 1. So I get negative 1, and the 2 factorial is 2. If I plug 1 into my third derivative, I get 2. And 3 factorial is 6, and that simplifies to 1/3. If I plug 1 into my fourth derivative, I'll get negative 6. And 4 factorial is 24, and that just becomes negative 1/4. So I said I just wanted to get up until A4. I'm going to plug all these coefficients into my Taylor series. So my Taylor series for ln of x here, well, the a naught is 0, and then I get plus 1 times x minus 1, minus 1/2 times x minus 1 squared, plus 1/3 times x minus 1 cubed, and then minus 1/4 times x minus 1 to the 4th. And I could keep going like this. Next up, it would be a plus and then dot, 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 because I notice that the signs are alternating. Okay, so I've written up until the first 4 coefficients and the plus dot, dot, dot. And I mentioned at the start, I want to practice putting this in sigma notation. So in sigma notation, I'd have this sum. And I notice all the terms have x minus 1 to a power, so I'll do like x minus 1 to the n. I could ignore this plus 0 here, so the first power should be a 1. And that's why I know I'm going to start at n equals 1. And now I need something for this denominator that shows up, and I need something for the alternating portion. Well, the denominator matches whatever power that I have. So in my sigma, if my power is n, that means the denominator's got to be an n. And then an alternator, it turns out I could either get an alternator with something like negative 1 to the n, or if I need to adjust the sign, I could do like negative 1 to the n plus 1. So I want to have you do a quick pause for 30 seconds, see if you can figure out which one of those it is. In 3, 2, 1, pause it and think about that. All right, so let's talk about it. If I plug in the starting value 1 into this, negative 1 to the 1 is negative. Ooh, but that doesn't match that I need a positive here. If I instead plug in 1 into this, I'll get negative 1 squared. Ooh, and that is positive. And if I plug 2 into this, I get negative 1 cubed. Oh, and that's negative. So that one's checking out. So this should be negative 1 to the n plus 1. And then it's got to go on to infinity. And there I have it. I did my first Taylor series example of something that's not just centered at x equals 0. This one was centered at 1.